Okay, couple things. If you are interested in talking to Lubrizol about internships, they'll be downstairs in the atrium after class and up to, I think, 10:30. They're going to be participating in the STEM fair next week. So if you have a resume already up and running, if you read the syllabus carefully, you actually would see that one of the assignments for the class is to have a resume approved by the Career Center at the end of the semester. That's like a quiz. So there is I think there's an online resource to help you do that. But anyway, they're in today. Then next week, I think there's like 13 companies that'll be here for STEM, for all areas of STEM. And Lubrizol is looking for both chemists and biologists because they do. One student who was in this class last year got an internship in their toxicology lab. So if you don't see them, today's an informal thing, just for them to chat. But next week they'll be here. So if you're interested in that, that's what's going on there. Okay. So chapter 5 on conformations of acyclic alkanes, and then what's today, Wednesday? Then Friday we'll talk about cyclohexanes. So I'll post a video on cyclohexanes at the beginning of that section after class sometime today. So when you go back into the chapter, it should be there for you to watch. From here on out, I have videos on all of these topics, but unfortunately I didn't have any up till this point. I mean, technically now for next year I have them, but that's next year, not this year. Okay, did anybody have any questions about this? I have plenty of problems that we can do. All right, let's jump right into problems then. Okay, all right, so one of the first things we have to do when we're talking about acyclic alkanes is we have to be able to take what's called a Sawhorse projection, and we have to be able to imagine ourselves over here looking down the carbon-carbon bond, and then writing that as what we call a Newman projection. So the Newman projection of this is going to tell us more about the spatial relationships of the groups on the ring, or on the two carbons. And so this is the first thing that we have to master. So let's say I put groups A, B, C, D, E, and F on the ring. Can you write the Newman projection looking at it from the left and put that into a Newman projection? So can you? If the answer is no, no. Say no. No, we should go over that, right? Okay, so let's go over that. So Newman projections are going to basically look like this. You're going to have a front carbon and you're going to have the back carbon. So the way the Newman projection works is that is the intersection of the three things that are attached to the front carbon, and then the big circle is the back carbon. And the way that we can look at this is we can do this. We can do this with the little models. And if you don't have models and would like a 2-carbon model, stop by my office. I can take one up. Well, if I'm going to say I'm going to take one up, then I better be able to take one up. So let's eliminate that. Let's see, we need to turn the light off. Then let me draw, so there's 2 carbons, and we'll go ahead and put that into 3D mode. Okay, so there is the model that I wrote. Because now you can see. So this is the structure that I just wrote with the carbon bond not being completely horizontal. But that's okay. So if you're looking at this model then, which I will take a picture of, because I'll put this in the folder. Maybe by this afternoon I can get that to come over here so I can capture it, but there's no guarantees. So that is the structure that basically looks like the ABC. So the critical part here is I determine what kind of Newman projection I should write by looking at the bonds that are in the plane of the board. I know you can't see that. Okay, so these are the bonds that are in the plane of the board. And so if you can imagine looking at A, B, and C, A is going to be straight up. So that this Newman projection is going to look like this. On the front carbon, A is straight up. B is behind the molecule and down, which now I'm looking at this carbon. You're the little stick figure now. You're looking at that carbon. So that means the B is off to the left if you're over here, and then C is right there. So that's the translation of A, B, and C when you're over on the left, looking down that carbon-carbon bond. Now, to reinforce that, if I come over here to my molecule, and I take this and I rotate it, I was over here to begin with, and now I'm going to rotate that molecule. So what you can see is you can see that the top carbon there, this and this and this are A, B, and C respectively. So that's what I see when I'm over here. That's my view. Can everybody kind of see that? Yes? Actually, I'll not only put these pictures in the canvas, but I'll put them in the book, in chapter 5 as well. All right, so now I got to go back here. Now, what about D, E, and F? Well, since F is in the plane of the screen and straight down, and A and F are opposite each other in that plane, F is there. So F is pointed straight down. And then there's a position here and a position here. So there's a number of ways to think about this. You could think about, hey, I'm over here looking there, so D is going to be on my right, so that's where D is going to be, and then E is going to be behind, which is to the left. And so there is the Newman projection looking from the left down the carbon-carbon bond of this. And the D and the C are both on bold wedges, and so you can see the D and the C are on the same side. Jennifer? And then the E and the B are both on dashed wedges, so the E and the B are on the same side. So these ones were on the dashed wedges, these ones were on the bold wedges. So that's how we convert what's called a staggered into a Newman projection. And I always work from the left on this. When I look at it, I look at it from the left. You could look at it from the right, and basically then the DEF carbon is going to be the front carbon, and the ABC carbon is going to be the back carbon. So it really doesn't matter which way you look at it. Okay. Right. Okay. Does everybody kind of see that? So then, because these groups are all at 60 degrees away from each other, their maximum distance away from each other, this is then called the staggered conformation. And so a conformation is different three-dimensional structures. So there's stereoisomers, and it's been, I don't know, probably 3 weeks since we've talked about stereoisomers. But EZ and cis-trans were examples of stereoisomers. And so this is a three-dimensional stereoisomer. But conformers are three-dimensional stereoisomers that can be formed by rotation around a single bond. And E and Z and cis or trans were just stereoisomers. They were not conformers. Right? So these are going to be conformers. This turns out to be the most stable of the two conformers of something like ethane. If all these groups are hydrogens, then this is the most stable conformation of ethane. Everybody with me? So then the other option that we have is to draw this structure, and these are actually what are called Sawhorse structures. I don't know if you've ever seen a sawhorse or know what a sawhorse is. A sawhorse is when you're cutting a piece of wood, you have these things called sawhorses that basically you have two of them and you place your piece of wood on them. Those are sawhorses. So this is called a sawhorse projection or a sawhorse structure. Now this one's different because in this case the bonds that are in the plane of the paper or the plane of the board or the plane of the screen make a U shape as opposed to a zigzag shape. And so if I have my groups A, B, C, D, E, and F here, and now again I'm over here looking down that carbon-carbon bond, I'm going to get a different Newman projection. The front carbon is going to look the same. So the front carbon's still going to have A at the top, B to the left, and C to the right. If again, I'm over here looking down that CC bond. And I'll go back to the iPad because I think it'll draw this automatically. But now what about D? In this drawing, D is in exactly the same plane as A. And so the way we do that is we draw the three bonds being in the same plane like that. Because technically, A is obscuring D. right? I can't see D because A is in front of it and blocking it. So we just kind of write bonds out to the side. Sometimes you'll see these bonds get a little bit farther away, but at some point it's too confusing. So I usually just write them parallel and very close. So that means A and D, C and F, and B and E are all in the same plane. So this would be the Newman projection. This is then going to be the Newman projection of that conformation. And there's two distinct conformations for a 2-carbon ethane molecule. They're either what we had before, which was called staggered, where the groups are away from each other, or this is called eclipsed. And what we have to remember about this is that whatever groups A, B, and C, and D, and E, and F are, they're atoms. As atoms, they're huge clouds of electron density. And whenever you get two big clouds of electron density as close together as possible, there's going to be repulsion. So this is going to be the least stable of the two conformations. So staggered's the most stable, eclipsed is the least stable. Does that make sense in terms of paper? So let's see if I can do it over here. Oh, let's see, let's download that. Okay, so there is what kind of conformation? That's staggered. So let's see, what do I have? Do I have some energy? No. So there's the staggered. No. Nope, I didn't want that. That's what. Okay. There's two different conformations, and they are basically about 4 kilojoules difference. So this is the most stable one, which is this one. And then up here, there's supposed to be a red line that I could press to get the second one. Why can't I do that? There. Nope, that didn't help. That's strange. So anyway, there is. If I can't put this into the eclipse mode because it's too high energy. And this thing only knows the most stable ones, apparently. But we'll come back and we'll put some groups on there, and then I'm sure it will work. Or I'm sure I'll try and make it work. Right. So that's the basics. Is everybody kind of okay with that? Are we bored with that? Do we need to go on to substituted ethanes? Sure. We can go on to a simple substituted ethane, which is, let's do butane. So if I said, hey, I would like you to draw the staggered and the eclipse conformations of butane. Yeah. It's okay. So let's do butane. But I always have to tell you what bond to look down. Because if I just give you a freebie, if I don't tell you what bond to look down, I'm looking down the carbon-1, carbon-2 bond. Because then I've got 3 hydrogens and it makes the problem really simple. So I'm going to say, let's look down to C2, C3 bond. Well, what does that mean? That means let's number this according to the IUPAC rules. So I want to look down the carbon-2, carbon-3 bond. So let's start with staggered. Let's start with a staggered conformation. And so what I like to do is I like to draw out all 3 of my staggered conformations. So I'll draw 3 empty ones. I'm going to decide what's the front carbon and what's the back carbon. Does it matter? Not in this case because it's symmetrical. Okay, so now I've got a problem. So I have to figure out what's attached to the front carbon. Remember, the front carbon is carbon 2. So what's attached to that front carbon? What's attached to carbon 2? What 3 groups? A methyl group and 2 hydrogens. Now, carbon 3 is also attached to carbon 2, but in this structure, carbon 3 is the big circle. So I don't have to include it. So what I have attached to carbon 2 is 2 H's and a C. And then carbon 3. So let's put them in. Methyl, hydrogen, hydrogen. Does it matter where I put them? No. Because what I'm going to do is I'm going to basically rotate around I'm going to rotate around the bond so it doesn't matter. Bless you. And now what's attached to carbon 3, the back carbon? The front carbon, number 2, and what else? What's attached to carbon 3? 2 H's and another methyl group. Now, somebody said carbon. I like to keep the groups intact. So I like to say 2 hydrogens and a methyl, because maybe there's an ethyl group there. I'm going to want to write down the ethyl, the entire ethyl group. So, attached to the back carbon is a methyl and 2 hydrogens. Doesn't matter where they go. No, because what I'm going to do is I'm going to rotate and generate all of the 3 possibilities. Right. So the first thing you've got to be able to do is draw the correct Newman projection. And so you have to get comfortable with, okay, the back carbon has 2 H's and a methyl, the front carbon 2 H's and a methyl. So now what am I going to do? Well, to generate the 3 possible structures, what I'm going to need to do is I'm going to need to hold one carbon constant and rotate the other carbon. I like to keep the front carbon constant and then rotate the back carbon. If you want to be different, you can go ahead and do that. But the critical part is you're only rotating one carbon. Because if you start rotating both carbons, there's no guarantee that you'll generate all 3 of the different conformations of the Newman projections. So that makes it relatively simple. I just take the front carbon and I go ahead and I write in exactly the same position my methyl and my 2 hydrogens. And now for the back carbon, I'm going to rotate this methyl down here. I'm going to rotate that hydrogen up there, and I'm going to rotate the hydrogen over here. So I'm going to make a 120-degree rotation. And so now my methyl group comes down to the bottom, my hydrogen goes to here, and my other hydrogen goes there. And now I'm going to do that one more time. So I'm going to take the methyl group, rotate it up there, then the hydrogen here and the hydrogen there. So I'm just going to make one more 120-degree rotation. And so now what I've done is now I've generated all three of the staggered conformations. Does that make sense to everybody? I mean, hopefully everybody's just like bored. Go on to something more difficult. But nobody's saying that, so we'll just continue on. Okay. Let's write the three eclipsed. So if I'm going to do my three eclipsed, I'm going to draw three eclipsed conformations. So I'm going to draw three blank eclipse conformations. And then I like to keep the front carbon in exactly the same position as they were in the eclipsed. In the staggered. So I'm going to write my CH3 at the top on the front carbon, then my two H's on the left and right bottom positions, like this. And what I'm going to ask you to do for these kinds of problems is, I'm going to give you a molecule, I'm going to give you a bond, and I'm going to say write the three staggered, three eclipse conformations for that molecule looking down the C something bond. And then I'm going to ask you to rank them, but let's draw out the eclipse first. And then we'll go ahead and think about energies. Now, how do I get the staggered into the eclipsed? I just need a 30-degree rotation to line up the groups. So you can go clockwise or counterclockwise here. Right? So I, for instance, could line up the CH3s and then line up the hydrogens by taking that CH3 and rotating it counterclockwise 30 degrees. And now I'm going to do the same thing I did before. Make 120-degree rotations. Again, clockwise or counterclockwise, doesn't matter, your choice, but you got to be consistent. So I'm going to make a clockwise rotation of the methyl. So I'm going to bring the methyl down here. This hydrogen goes over here, and this hydrogen comes up here. So there's eclipse conformation number 2. And then finally do that one more time. The CH3 comes over here, and there's my 2 hydrogens. So again, I'm making 3 120-degree rotations. Okay. So now, are we confident about energies? If I pull up the clicker and ask you to say which one of these is the most stable, or are there any 2 conformations that have the same energies, could we do that? Or do we need to know the rules? What? Rules. Okay? Because there's always rules. So what are the rules about staggered and eclipsed conformations? All right, well, we will write these down and make them state law. Rules number 1 is that staggered are always more stable than eclipsed. And what does that mean? That means that the least stable staggered is more stable than the most stable eclipsed. So if I'm going to rank these from number 1 to 6, 1, 2, and 3 will always come from the staggered, and 4, 5, and 6 will always come from the eclipsed. Okay, that's rule number 1. Rule number 2 is that you want less gauche interactions or less eclipsing. interactions, depending on whether you're in the staggered or the eclipse. Now, what does that mean? What is gauche? Gauche is when two non-hydrogen groups are next to each other in a staggered conformation. So I'll come over here. These two methyl groups, they are gauche to each other. So gauche means the two groups are next to each other in the staggered conformation. And that's as close as they're going to get in the staggered conformation. So when two groups are gauche, that's an unstable interaction. When they are, in this case, what is called anti, when they're opposite each other, that's the most stable situation. So if I'm gonna look for energies, what I'm gonna say is I want the least number of gauche interactions first. Okay. This one's easy because there's only one gauche interaction. But that one gauche interaction is more than B has with 0 gauche interactions. Okay. So another way to say that is more gauche interactions, more unstable the molecule. In eclipsing, these two methyl groups, those are eclipsing. And so the more eclipsing the interactions, the greater the energy and the more unstable the molecule. All right, so that's the second rule. And these rules are going down according to sort of priorities. But they're getting more detailed as they go down. So rule number 3 then is that when we're looking at gauche or eclipsing interactions, the bigger the groups, the more unstable the interaction. So for gauche or for eclipsing, the larger the group, the more unstable the interaction. And what that means is that if you had a methyl and an ethyl group gauche, that would be bad, but it's not as bad as an ethyl group. So methyl and ethyl is bad, but ethyl is even worse. So the bigger the groups that are involved in the interactions, the more unstable the molecule. And again, why is that? Because these are big clouds of electron density. The bigger the group, the bigger the cloud, the more they're going to repel each other. And that repulsion is called steric interaction. That's what we call sterics. So when alkyl groups are next to each other, that's sterics. So if we follow those 3 rules, we'll be able to rank these molecules according to their energies. Do those make sense? So if we apply them here, which conformation is the most stable overall? B? We're all in agreement that B is the most stable? Then what about next most stable? Well, your 2 choices are A and C. They have the same energy. So A and C have the same energy. Okay, I'm going to make a very big distinction here between they're the same and they have the same energy. they're the same means that they would have the same exact structure, which they do, except they're like backwards. So I'm not going to consider backwards to be the same. So they have the same energy. So A and C would be tied because they have the same energy. Then of D, E, and F, which one is the least stable of D, E, and F? D. So D has both methyl groups eclipsing. That's bad. And so that's less stable. And then what about E and F? Same energy. So notice that your best case scenario is to have a group gauche to a hydrogen or a group eclipsing a hydrogen. They have to be eclipsing something, so the best case scenario is they're eclipsing the small hydrogen. But anything above that is going to cost you an energy. So that's what I'm going to ask you to do and be able to recognize with these conformations. Is, can we write all 6 and can we rank them? Now I think for the butane, I can do this. I think there's a picture of it in your book. Okay, so here's my butane. Looking at it from that perspective, so I'm looking down the carbon-carbon bond. Which one is that?
If you're looking at the 2 center ones?
I'm looking at the 2 center ones right here that are right there. Are they staggered or eclipsed? Here, let me do this. That probably didn't help. What do they look like?
Is it B?
That looks like B. That's the staggered with the 2 methyls opposite each other. You have to get your frame of reference on this, so what I'd have to do is what did you just do? So let me see if I can do this one. All right, so I brought that down. Now I'm going to do the rotations. But I have a grand total of 2 energies. Let's see what it says. There's the first one, and there's the second one. So which one is this? Staggered or eclipsed? I'll tell you it's staggered. So this is the one where the 2 methyl groups are gauche. These are the ones with 2 methyl groups are gauche. So if I did a calculation on the computer, this molecule is a little over 3 kilojoules more unstable than the anti, because that's what the bar on the left is telling me. And then you'd say, well, so what? And then I would say, well, we could actually put this molecule into those 2 conformations into percentages. If we go back to general chemistry, which we really don't want to do, and remember that delta G equals minus RT ln K, and that energy difference of 3.2 kilojoules, if we plug that in as the difference in energy, then we could calculate a K value, which is the equilibrium constant, and then we could put that into percentages, which we're not going to do right at the moment, but we will at the end of the year when we do some computational stuff. So, needless to say, and I have a sheet that I don't remember. What you need is a sheet of energies and a sheet of K's and a sheet of percentages, which maybe I'll bring on Friday. But if you want to think in terms of how much percentage is anti and how much percentage is gauche, that's how we'd have to do it. We'd have to figure out the energy and then do general chemistry. But that's what it would look like. Okay. All right. So this is the process. Then the question is, all right, give me another problem. Okay. And I do have some homework problems that have mysteriously disappeared or they're hiding from me on Canvas, but I will find them. Because I have some problems where I give you the name and ask you to write all the Newman projections and then rank them. And fortunately, it has an narrated answer key, so I don't have to go back and do that again. But I need to find that file. And it's got to be in a previous year. But anyway, that's my problem. So let's say, what do I want to do here? How difficult do I want to make this? Let's start with a hexane. And let's see. Okay, so let's say we have 3,4 dimethyl hexane. And I want you to look down the C3C4 bond. Can you write all of the staggereds, all of the eclipse conformations, and then rank them in energy from number 1 to number 6, indicating any ties where appropriate? So what are you going to have to do? You got to draw it out first, and then you got to transfer that drawing into a Newman projection. And since we only have 3 minutes left, I think this would make an excellent take-home quiz problem for you to do and then bring to class on Friday on a piece of paper and hand in so that I can grade it. Is what I think. Because I haven't done that so far this semester and we need to. Okay. All right, so that's going to be your take-home quiz. Is to draw the structure, convert it to Newman projections, staggered and eclipsed, and then rank those from number 1 to number 6. And we'll make that, and I'll collect that up at the beginning of class on Friday. So let's see.